All right, greetings math people. In this particular video, we're going to address a misconception about one of the properties of limits, and that is something that you may call the product rule, where you have the limit of the product of two functions. So let's go ahead and get right into it.
Specialized in science and math, original black men, busting thoughts that pierce your mental, the fierce, ripping your section, vocal toe to toe, impeccable, splitting your back, son. Simple as addition and subtraction, black thought, the infinite relax one.
All right, so here is our issue. So we were all taught, when we were taught the properties of limits, how to deal with the limit of the product of two functions. And so it goes as so. Say you have a function f, and the limit as x goes to c of f of x equals L. And you have a function g, and the limit as x goes to c of g of x equals k. And so therefore, the limit of f times g as x goes to c is L times k. So the limit of a product is the product of the limits. The problem is that particular property doesn't always hold. And sometimes when we learn it, we think it's a universal, omnipresent property that will always hold. But there are cases where that property doesn't hold. And there's a more effective way of looking at the limit of products other than the property that we just talked about. So let's look at an example. So let's think about a problem, and in this particular problem that the product will hold, and then we'll look at a couple of examples where the property holds, and we'll look at a couple of examples where the property doesn't hold. So let's say we're going to take the limit as x goes to 2 of x squared times the tangent of pi x over 8. So we're taking the limit as x goes to 2 of x squared times the tangent of pi x over 8. Now this obviously can be viewed as a limit of the product of two functions, where you can consider one function x squared and the other function the tangent of pi x over 8. And we can take both of those limits independently and just find a product of those two limits. So of course the limit of x squared as x goes to 4 is 16. And the limit of tan of pi x over, the limit of x squared as x goes to 2, we're taking the limit as x goes to 2, pardon me. The limit of x squared as x goes to 2 is 4. And the limit of the tangent of pi x over 8 as x goes to 2 is 1. And so one limit is 2 and one limit is 4 and the other limit is 1. And so the product of those two limits is 4. And here I'm showing the graph of that function. So the graph you're looking at now is the total function x squared times the tangent of pi x over 8. And from a graphical standpoint, you can easily see as you come from the left and the right that the limit as x goes to 2 obviously equals 4. And what we just did is really the most effective way of looking at the limit of a product of two functions versus finding the limit of each function and then having a product of the limits. And the problem with that particular process is sometimes the limit of one of the functions or both of the functions may not exist. And when those situations arise, then the property that we just talked about, the limit as x goes to c of f times g is just a product of those two limits of f and g independently. It doesn't work when one of the limits doesn't exist. And yes, it is incorrect to assume if the limit of one of the products doesn't exist, the whole limit doesn't exist. And that's a big misconception many people have. So a lot of people will follow this product rule property of limits as the holy gospel. And then when they get one of the functions or maybe even both of the functions limit not exist, they think the whole limit doesn't exist. And the rationale is, say one limit was 4 and the other limit didn't exist. 4 times doesn't exist equals doesn't exist. Or both limits don't exist, and of course don't exist times don't exist just means don't exist. The problem is that's not always the case. So you can have the limit of a product of two functions and one or more of the limits, the limit of one of the functions or even both of the functions cannot exist, but the limit of the product actually could exist. Let me give you an example to illustrate this point. And as I'll show in this example, the best way to look at finding limits of a product. So let's say one function is 6x minus 30, and the other function is 1 over x minus 5. So one function is 6x minus 30, the other function is 1 over x minus 5, and let's say we're finding the limit of both the product of those two functions as x goes to 5. So if you just multiply those two functions, 6x minus 30 times 1 over x minus 5, you can just say it's 6x minus 30 over x minus 5. And if you look at each limit independently, the limit as x goes to 5 of 6x minus 30, that limit would equal 0. And the limit as x goes to 5 of 1 over x minus 5, that limit doesn't exist. So one limit is 0 and the other limit doesn't even exist. So does that mean that the limit of the function, the limit as x goes to 5 of the function 6x minus 30 over x minus 5 doesn't exist? No, it doesn't, because the limit does exist and the limit is not 0. So you may think, okay, it's a special case. One limit was 0. You might say, okay, well, 0 times does not exist. It's going to equal 0. Well, actually, the limit of the function is not 0. The limit of the function, so the limit of 6x minus 30 over x minus 5 as x goes to 5 actually equals 6. And, the easiest way to do it is, again, is not to look at it as two independent functions, but look at the function as a whole. And if you just think about it algebraically, 6x minus 30 is 6 times x minus 5. So 6 times x minus 5 over x minus 5 is just 6. It's just a horizontal line at y equals 6. And so the limit of those two functions is simply 6. So there's one case where we had a limit of a product, and some of you may think that's not really a product, it was a quotient, but it was a product. One function was 6x minus 30, and the other function was 1 over x minus 5. And so there we showed an indication where you find a limit of the product. One of those limits didn't exist, of one of the product functions didn't exist, but the limit of the overall product did exist. So what we're presenting here is, in most cases, it's best to look at the product as a whole if you're able to do the algebra like we just did, or able to look at it from a graphical or numerical standpoint. It's probably best to look at just the product function itself versus breaking it up into two different functions. Let's look at another example. So let's say we have the limit as x goes to pi over 2 of tan x times cosine x. So we have the limit as x goes to pi over 2 of tan x times cosine x. Okay, product of two functions. Let's look at both those functions independently. So the limit of tan x as x goes to pi over 2 does not exist. The limit of cosine x as x goes to pi over 2 is 0. And all cases are not going to be does not exist times 0. This one just, again, happens to be does not exist in 0. And yes, the limit of this function does exist, and no, the limit isn't 0. And so if you think about it, tangent times cosine is sine. And the limit as x goes to pi over 2 of sine x is 1. So I bring this up because what happens later on for the calculus students, they could be doing something like improper integrals and get into the point where they're finding the limit, and then they have the limit of some product, and they will sometimes look at it as each function independently and find the limit of one or both of those guys does not exist, and then falsely conclude that the limit as a whole doesn't exist. And so the function, the limit diverges, and therefore the improper integral doesn't exist. It diverges, which is really not the case. And so when looking at limits of a product, Now, if both, so I'm looking at the limit as x goes to c of f times g. If both the limit as x goes to c of f and the limit as x goes to c of g exists, then the elementary property that you learned first is fine. But if one or both of those functions limit does not exist, you have to look at the limit of the product function as a whole and simplify the function as you can to do the analysis. Again, in the little two examples we looked at, 6x minus 30 over x minus 5 kind of just simplifies to 6. Tan x times cosine x just simplifies to sine x. And so if there's a way to algebraically simplify the function, go ahead and do it. And then of course, when simplifying some functions, when simplifying 6x minus 30 over x minus 5, there's a removable discontinuity there. But however, removable discontinuities don't affect the value of limits. So in the simplification process, we could encounter removable discontinuities, but we must remember that they have no effect on the value of limits. So that was my little take on misconception we see sometimes about the limit of the product of two functions, and we will see you next time.
Specialized in science and math, original black men, busting thoughts that pierce your mental, the fierce, ripping your section, vocal toe to toe, impeccable, splitting your back, son. Simple as addition and subtraction, black thought, the infinite relax one.